Okay. All right, so we've finished the quiz. Gave you guys your quizzes back. Let's talk about concavity and inflection points, which is what we learned last time. The lesson from the other day can probably be summarized. What happened? Do I? Thank you. Oh, I do. Got caught in my... It's probably from fuzz from my pocket or something. Maybe it was food. Thank you. Is that just a normal video thing before I just... Yeah. It's like, well, just let it go for as long as you can. See when he finally realizes it. Yeah. Well, thank you for telling me it was there, implying that you at least like me a little bit. So, all right. So we can sum up the entire lesson that we learned the other day, and this will be good for you, Jasmine, given that you weren't here, in 3 statements about concavity and inflection points. Okay. Can anybody think of one statement that if someone knew this, in fact, before we say those statements, let me say something else about concavity and inflection points. A person can successfully answer lots of questions correctly about concavity and inflection points without fully understanding concavity and inflection points. Now, I don't recommend it, but the fact of the matter is that the rules for being able to identify inflection points and concavity are reasonably simple. Okay? And that if you know how to identify concavity and inflection points analytically, on a graph, with numerical values, then you could be just fine. Now, you should have an understanding of these things, but you can still answer questions without having a strong understanding. And if a person knew these 3 basic rules or these 3 basic statements, they would be able to answer pretty much any question about concavity and inflection points. You think you have an idea about what one of them is? Give it a shot.
Does it have anything to do with maximum and minimum?
Not so much. No, it has more because maximums and minimums don't tell us how to identify concavity really. I mean, they would on the first derivative, maximums and minimums could help us. Okay, but now you're going into a deeper understanding, which is good. Now, and we'll get to that in just a little bit. But what I mean is this: I know. Here's the first statement. I know that a function is concave down if.
Does signs change?
The second derivative is
Greater than 0.
less than 0, negative. That's right. First statement. I know a function is concave down. That I know that its graph is concave down if its second derivative is negative. First statement. Second statement.
It's concave up if the second derivative is positive.
There you go. That I know that the graph of a function will be concave up if its second derivative is positive. Okay? And the third statement regards inflection points.
Inflection point is when the sign switch?
Yes. I know that a function has an inflection point if the second derivative is 0 and changes from positive to negative or negative to positive. Okay? If you have a sign change on the second derivative and it includes a 0, okay? Meaning you don't have a jump discontinuity. That's not the kind of sign change I'm talking about. Okay? So if the second derivative is 0, but you do not have a sign change, it is not an inflection point. Okay? So with those 3 statements, you can answer just about any question about concavity and inflection points. And what I want to do is I want to look at, from your homework, question number 8 said this. It says identify if your function, if we got a function, y equals negative x to the 4th, okay, negative x to the 4th, plus 4x to the 3rd, minus 4x plus 1. Okay? If you have this function and you want to identify where this function is concave up and where it is concave down, what do? Find the first derivative first. Okay, so y prime is negative 4x cubed plus 12x squared minus 4.
And then you do the second.
Find the second derivative. Y double prime negative 12x squared plus 24x. Okay? All right, and then what do we do with this?
Solve for the R0.
Yeah, find the 0 where it equals 0, right? Okay, we're going to set it equal to 0. And one technique we could use is we can factor, right? There's actually a greatest common factor, right? All right, 12x. But what's that? I wouldn't do 6. I would do 12. Well, if we take 12 or if we take 6 out, we leave a 2 here and we leave a 4 here. 2 and 4 still have a common factor, which is 2. Does that make sense? Okay. Now, it wouldn't really matter. Actually, you could just take x out and then set what's left over equal to 0 and solve it. It's linear at that point, so it doesn't really matter. Okay? One way or the other, it doesn't really matter. Okay, but I will say this. I don't know if you were taught this when you were taught how to take out a greatest common factor, and I don't know how much time your teacher spent on greatest common factor. Back in the day, they would spend a week on the greatest common factor. You would do 100 different problems where you take out the greatest common factor. And the reason for that is, back in the day, we understood how important the greatest common factor was. Nowadays, they rush you through greatest common factor in like half a period or something, and then they teach you something else, and you might even forget what a greatest common factor is. Okay? But I'll say this. When you are taking out a greatest common factor, I want you to consider this. Whatever your lead coefficient is, in this case, the lead coefficient is negative 12. If your lead coefficient is negative, take out the negative. That's right. When you're taking out a greatest common factor, if the lead coefficient is negative, take out the negative. Because whatever is left over, you may want to do something important with it, and it is not easy to do something important with a polynomial that starts with a negative. Okay? So instead of taking out 12x, we're going to take out negative 12x. If we take out, so now y double prime is going to be equal to negative 12x. And if we divide, so that leaves x. And if we take negative 12x out of here, we have left negative 2, right? Okay? And isn't it much nicer to deal with x minus 2 than negative x plus 2? Okay? And now this is equal to 0. Now it's really simple. If we make a sign chart, what are our zeros? 0, indicated by an x with no plus or minus. And then what did you say? Positive 2. That's correct. Okay? So our zeros are 0 and positive 2. And now, in order to be able to identify concavity, what do we need to know?
Negative or positive.
Yes, plug in numbers, right, greater than or less than these numbers, and find out on these intervals where it is negative or positive. Okay, so we're going to plug it into the second derivative. So if we plug in negative 1 minus 2 is a negative value. Negative 1 times negative 12 is a positive value. And so a positive times a negative is a negative. Okay? All right? If we plug 1 in, 1 minus 2 is a negative value. 1 times negative 12 is also a negative value. Negative times a negative is a positive. And lastly, plug in 3. 3 minus 2 is a positive value. 3 times negative 12 is a negative value. So we have a negative value. And so now our sign chart indicates that our second derivative at values less than 0, at x values less than 0, our second derivative is negative. Between 0 and 2, our second derivative is positive, and at values greater than 2, our second derivative is negative. So somebody give me an interval where this is concave up? Where y is concave up, not y double prime, y. Yes, so from 0 to 2. So we are concave up on the interval 0, where x is between 0 and 2. Okay. What about concave down? Down. And another way to say that is for all values of x less than 0 and all values of x greater than 2. There we go. Okay? Yeah, that'd be fine. Yeah, it'd be the same. And if somebody said, hey, sketch this graph, sketch the graph of y. It'd be a really rough sketch, but you could do this. You could go to 0, and you could go to 2, right? And then you can just draw a graph that is concave down. Now, we're not sure what it looks like, but let's say it's concave down. And then from 0 to 2, it's concave up. And from 2 to infinity, it's concave down. Is that unreasonable? Does this look like an x to the 4th graph that has a negative lead coefficient? Yeah. It's probably wrong. But based only on the second derivative, it's not bad. If we set the first derivative equal to 0 and then found out where the maximums and minimums were, then we could make a more precise graph. Does that make sense? Okay. So there's an example of an analytical problem where we identify where it's concave up, concave down. And by the way, inflection points. 0 and 2 are both inflection points. What if this was a plus? Just 0. 0 would be the only inflection point. 2 would not be an inflection point. This would be an example where it is concave up and then no concavity for one instant and then concave up again. So you wouldn't even be able to see it. You wouldn't even be able to see it on a graph. Okay. Okay. All right, let's do a graphical problem now. In your textbook we have questions 21 and 22. I think we did these the other day. This is page 215. Question number 22 right here. And this is what it says. It says use the graph of the function to estimate where f prime and f double prime are 0, positive, and negative. Okay, I don't really want to talk about f prime. Let's just talk about f double prime for now. Okay, so looking at this graph right here, this is f of x. This is not the first derivative. This is not the second derivative. Okay, can you guess, and you're really going to have to approximate because it's very hard to see exactly where, but can you give me an approximation on where f double prime of x, where f double prime of x is equal to 0? Negative 1. Okay, negative 1 would be right about here. That's not unreasonable. Are you looking for here?
Yeah.
Okay, that would not be where.
Okay.
Yeah, this is where the first derivative equals 0. Slope.
Okay.
What is f double prime of x or f double prime of x equals 0? Right, it's the rate of change of the slope. So the rate of change in the slope is 0. Okay, and what happens generally where f double prime of x is equal to 0? What's that?
It'll be a 0 on it.
The slope of the slope. So if
Yes,
slope equals 0,
but graphically, what happens? Not a vertical tangent line. I can see. Oh, I thought that's what you were saying. Sorry.
I don't know.
Well, we just did a problem, and you affirmed to me that something was happening at 0 and 2. Yes, this is this. We just created a sign chart of the second derivative. I asked you questions about where it's concave up. I asked you questions about concave down. And then we wrapped up with an affirmation that something was happening at 0 and 2. Yes, sign change.
Inflection point.
Inflection points.
So the inflection points are the
Right.
looking for.
Yes, you are looking for, if you're looking for where f double prime of x is equal to 0, you are visually looking for an inflection point.
So it's like
What's that? Not 0, because at 0 it's clearly concave down.
it's like 1/2.
Yeah.
Negative 2 and 2. How about 0.5?
Yeah. Points, yeah. 0.5 is a good approximation, and where else? And negative 0.5. See what's happening here? Tell me about it, about the concavity right here. This is concave up. Think about it as a cup. Okay? Can this hold water? Only cups held up can hold water. When you turn a cup upside down, it can't hold water anymore. Okay? So, you turn the cup upside down, concave down. Okay? So, concave up, concave down. Well, in order to go, how are you going to go from concave up to concave down? You have to have an inflection point. Okay? Tell me about the second derivative right around here. Greater than 0, that's right. Is Randy the only one who remembers that?
One more time. I didn't see where you're going. I just like went
Here.
for a second.
Okay, between negative 2 and from negative 2 up to about 1. It's concave up, which means the second derivative is greater than 0. Okay? So, and here it's concave, at around 0, it's concave down, which means that the second derivative is less than 0. To go from greater than 0 to less than 0, it's going to have to be equal to 0. So somewhere in here, f double prime equals 0, an inflection point. Okay? So when it says approximate, you're going to guess. So let's say negative 0.5. Is that unreasonable? Okay. All right.
Negative and positive.
And positive 0.5, because look, we go from concave down to concave up right here. Go ahead.
So technically it's like there will be a point that equals 0. The second derivative?
Second derivative equals 0.
Between where it's concave up and concave down.
Correct. That's exactly right. So the first part of the question says identify where f double prime of x equals 0. Okay? The next part of the question says identify where f double prime of x is positive, is greater than 0. Yes, okay, negative 2. And I mean, someone might say from negative infinity. It doesn't matter. But negative 2 up to not 0. Yeah, negative 0.5, wherever you approximated the inflection point was. Where else? Where is f double prime of x positive? Greater than 0.
Isn't it from like 0.5 to
0.5, yep, that's exactly right. Everywhere you see upward concavity, f double prime of x is greater than 0. And so now the other part of the question, last part of the question says, where is f double prime of x less than 0?
negative 0.5 to positive 0.5?
Correct, there we go. Okay? There's going to be a question like that on the quiz. It's not. It's all there. What you're trying to do here is you're trying to make a connection between something analytical and graphical. That's correct. Okay? Can somebody open that? Is that Bianca? Okay, great.
So we're only saying that that's concave up because that's how the graph of y f or y.
Say that one more time.
So wait, it's going down, but like it's concaving up because that's only
Yes.
the graph. So that's not the derivative.
No, look, see what we're looking at? This is actually the original graph. Always very important for you to look at, to ask yourself the question, what am I looking at? Am I looking at the first derivative? Am I looking at the original function? Or am I looking at the second derivative? You have to ask yourself that question. You okay? Thank you. All right. Yes?
Are second derivative graphs always linear?
No. Often when we talk about the original, an original function, if we say f of x is a cubic function, if we say that f of x is a cubic function, then the first derivative is going to be quadratic, and then the second derivative is going to be linear. That's just a common... Using the cubic quadratic linear is just a simple way of showing people the relationship among the three. Okay? But what is the derivative of sine? Cosine. F of x equals sine of x. F prime of x equals cosine of x. And f double prime is negative sine. Right? And that is not linear. Okay? All right, so that's that. Now let's look at another problem, and then maybe we'll have a chance to move. We're going to really dig into this problem right here, number 29. This is what the question says. It says that this is the position of an object. This is question number 29 on page 215. Okay, it says that this graph is the position of an object moving left and right along the x-axis. Or no, it's just a particle moving along a line. Okay, and it says at approximately what times is the particle's velocity equal to 0? So now we're actually not talking about second derivative.
That's just.
We're talking about the first derivative, right?
Time equals distance.
Yes. Distance and time. It's a position function.
No, I'm saying.
Yeah.
What was the question again?
Approximately when is the velocity equal to 0? Wherever the slope is 0. Sure. Yeah, somewhere around 6. Where else?
2.
Maybe around 2. Okay. And around 10. Now, we're not sure about over here. It just sort of tapers off. It might be 15, but let's say 10, 6, and 2. Are y'all with me on that? Okay. All right. And then it says, the next part of the question asks, at what time is the particle's acceleration equal to 0?
Derivative of
The second derivative. That's correct. What's that? Maybe 1. Depending on what's happening right here, yes, maybe 1. Okay? For sure, somewhere around 4. For sure.
Okay.
Maybe 1, but for sure around 4.
8.
Inflection points, that's right.
Those are 8.
Yes, 7 or 8.
Yeah, maybe 8. Yeah. It could be 7 because inflection points can be very close to the minimums. I would guess at 8 rather than 7. Okay? And then what's happening? Do you see what's going on? Yeah, there's definitely tell me about the concavity here. Down, right? Okay? Tell me about the concavity right here.
Might be going up.
No, it's pretty. If you look close enough at it, you'll see that it has a curve to it right here. Okay? So there's definitely inflection point somewhere around here. Okay? Dorothy, you look a little confused. Okay. But you're okay with the content? Yeah, maybe 13. Sure. Okay? All right, now I'm going to bend your brains a little bit. With all the information that you just gave me, can you tell me approximately, just give me one interval, an approximate interval, where this object is slowing down?
4?
From 2, well, I wouldn't say from 2 to 6.
3 to 4.
Because at 2, it stopped, and at 6, it stopped. So I'll give you that it's speeding up somewhere on that interval, or slowing down somewhere on that interval, but it's also speeding up somewhere on that interval.
3, between 3 and 4, 5?
Maybe 3 and 5?
I said 4.
Okay, you say 4, but why would we, 4 and 5, but will we stop at 5?
No.
It's still slowing down all the way up until it stopped, right?
So like.
Okay?
Oh, so then we do from the inflection point to the point of the
2 to 6.
Yes, from the inflection point. Let's think about this, though, without necessarily thinking about it as from inflection points. Watch this. Let's think about what's happening at 5. Look at 5. Can you tell me about the velocity at time 5?
Positive.
V of 5. V of 5. You say negative. Someone else said positive. Okay, why do most of you say it's negative?
The slope is negative.
Because the position has a negative slope. It is very clearly, the velocity is very clearly negative, right? What about the acceleration at time 5? What should we be looking at? Not the inflection point. That would be where it's 0. The what?
The average of position.
Yeah, but the word steepness is imprecise. Here we're talking about the slope is clearly negative. The concavity is going to tell us. What is the concavity at time 5? It's greater than 0. It's concave up, right? So analytically, looking at a graph, we're able to convert information from a graph into analytical information. Well, really, this is numerical information, actually, I should say. Into numerical information. And with this numerical information, at time 5, what is this object doing? It's slowing down. Okay? What direction is it moving? Left or down or whatever, the negative direction. The question has to tell you, oh, right is a positive. Think about the x-axis. The rightward direction is what? Positive or negative? Positive.
So the velocity will be determined whether or not it's going to the market.
Correct. That's exactly right. Yep, the sign of velocity. If velocity is a positive sign, that means that it is a positive direction. If it has a negative sign, it is a negative direction.
So, you said that this is going left?
I said that this is moving left, yes, because velocity is negative, less than 0.
Makes sense.
Do you see how you can look now that you understand concavity, now that you understand the second derivative, you can look at the graph of the position of an object and determine whether it's speeding up or slowing down just by looking at its slope and its concavity, because the slope and concavity give you the sign of both velocity and acceleration, which is all you need to determine whether the object is speeding up or slowing down at a particular time. You guys okay with that? All right. Can I bend your brain just a little more before we do the second derivative test? This is going to take 5 minutes at the most. Okay? Let me bend your brain just a little bit more. I want you to look at this graph again. Let's stay on this graph on page 215, number 29. Okay? I want you to pretend that this is the graph of velocity, not position. Okay? So we're going to pretend that this is not the position graph. We're now going to pretend that this is the velocity graph. Okay? Looking at this graph now, can you tell me where the position graph has inflection points? At the zero, what do you mean at the zeros? Be more specific. Where the slope is 0, because acceleration is the derivative of velocity. That's exactly right. Acceleration is the derivative of velocity, which means that acceleration is the slope of velocity. So if we want to know where, was that too much, Jasmine?
Okay, I just need to know.
Let me draw it up on the board.
I'm confused on
No, it's literally
where we're
the
going.
same thing. Because it's just the slope
Yeah.
of that, and we just changed this graph to
Velocity.
the derivative. So
Yes.
it's literally the same values that we did before.
Does something like that. Would you agree that's what this graph looks something like? And right here, that's a 6. We'll say right here, that's a 2. Somewhere, is that a 10? The maximum here? I know I sort of messed up there, but it's close, right? That's a 10. Okay?
Okay, so go over your question.
Okay, so here's the thing. We are now going to say that this is the velocity of the object, not its position. Okay? And I want to know where the position graph has an inflection point. Okay? Now, what would you be looking for to find an inflection point? Analytically, what would you be looking for? When what is the slope of what? Well, let's start over. Let's think. No, because you're going an extra step.
Okay.
Overall, what's the basic? Remember I said 3 statements. right? One of the statements was, how do we know when and where inflection points are?
The sign change.
On what?
The second derivative.
On the second derivative. In position, velocity, acceleration, which one of those is the second derivative? Acceleration, okay? So we want to know where acceleration has a sign change, right? Where it either goes from,
Okay.
and this is velocity.
So we just would go one more.
Yes, so acceleration is the slope of velocity. So wherever velocity has a slope of 0,
Second.
the second derivative has a value of 0. So where are the inflection points? 2, 6, and 10. That makes sense now? Now, remember though that it's not just where the second derivative is 0, but where it changes sign. Does acceleration change signs at 2? Yes. What is acceleration prior to 2? Positive. And after 2? Negative. Prior to 6? Negative. After 6? Positive. Prior to 10? After 10? Negative. Okay. It makes sense though, doesn't it? Now, one more question. Where then is the position graph concave down? There's a couple places. Can you tell me one place where it is concave down?
I want to say like 4. But I think
Sure, but I need an interval. I want an interval.
Oh, in the interval 2 to 6.
2 to 6, right. Because the slope of velocity is negative, therefore acceleration, the second derivative, is negative. Yeah.
Okay.
Concave down on the position function. Does that help a little bit? Okay. All right. So that is, they love tying in the shapes of graph stuff in with velocity, acceleration, and position. Object motion, the graphs of object motion are a popular topic on the AP exam. Yeah, they're very popular. Now see, you don't know what very popular means on the AP exam really, because if you take the AP exam, when you take the AP exam, you'll see like 1 or 2 of them. You'll be like, that's not that popular. When you look, if you look, and I would encourage you to do this, look at the tests over the past 20 years and look at the questions they have asked. Every year they have a graphical question that has something to do with object motion, either in multiple choice or in free response. They love it. Okay? Whereas some kinds of questions they only ask every couple years or every few years, certain types of questions, that the object motion with the graphs and the object motion with the sometimes they also really love the numerical object motion questions. Okay, let's talk about the second derivative test. We've got about 10 minutes left. Some of you only have 5 minutes left. Let's talk about the second derivative test. I'm going to draw a graph. Yes, sir. Oh, distraction? Okay. I'm going to draw a graph, and I'm going to ask you some questions about it, okay? All right. Okay. We're going to call this point right here A. We're going to call this point here B. We're going to call this point here C. We're going to call this point here D. Oops, that's an A. I did that yesterday too, only I wrote a Q instead of a D. I must be messing issues in my brain writing out the D's on the board. A 9, that was it. Yes, it was you guys. I wrote a 9. Maybe it's just your class. Is somebody in here transmitting their ESP during class? You guys are supposed to turn your ESP off during class. Extrasensory perception? You guys are messing with my brain. It's like my Wi-Fi network up here is picking up signals that are, yeah, okay. All right. Now, here's what I'm going to ask you. Y'all, everyone look up at this graph, and I want you guys, I want to make sure everybody is in agreement here, because until everyone is in agreement, I'm not going to write it down. Tell me about the second derivative at point A.
Is that position time graph?
Concave up, okay?
Wait, is that position?
Greater than 0. What's that? Oh, I'm sorry. Good question. This is f of x. This is f of x. Okay, so tell me about the second derivative at point A.
It's, oh man, the sign changes.
Okay, what's the shape?
Concave up.
Concave up, right? So f double prime of x is positive, right? Greater than 0. What about at point B? Concave down, so f double prime of x is less than 0, right? What about at C? Concave up, f double prime of x is greater than 0. And at D? Concave down, so f double prime of x is less than 0. Okay? All right, now, tell me about the first derivative at A. F prime of x equals 0, indicating a possible, not inflection, no. Minimum or maximum. How would you characterize A? As a minimum, a local minimum. How about at B? F prime of x equals 0, minimum or maximum? Maximum. How about at C? F prime of x equals 0, local minimum. How about at D? Equals 0, and it's a maximum. The second derivative test is actually the second derivative test for identifying relative minimums and maximums. Now I want you to look very closely. I want you to compare whether it's a minimum or a maximum to its second derivative. Tell me if you notice a pattern.
When it's a minimum, the second derivative.
It's negative when it's a maximum.
Yes.
And positive when it's a minimum.
Correct. You cannot have a maximum unless it is concave down.
Oh,
Maximums are always concave down. Local minimums are always concave up. I like the second derivative test better than the first derivative test because with the first derivative test, I have to know what the slope is. I need two numbers, one on each side. But for the second derivative, all I have to do is, if I know that f prime of x equals 0, like let's say that f prime on a function, f prime of 5 equals 0, and I know that f double prime of 5 equals 7. Is that a local minimum or a local maximum?
Minimum.
Why is it a minimum?
Because it's greater than 0.
Yeah, it means it's concave up. It has this shape. We have a slope of 0 and a concave up shape indicating a minimum. What's that?
I actually get the graph.
That's it. Yep, that's exactly right. That is the second derivative test. Okay? You guys can go ahead and take off. I am going to cover one more thing, so I recommend you watch the last 5 minutes of the video. Okay? All right. So now, what if f of 0 is, or f of 5 is 0, and f double prime is negative 3? It's concave down, has a slope of 0. So what does that indicate? That's a maximum, right? So you don't even need the graph. You don't need the whole derivative. Let's say you only know anything about the second derivative, but they do tell you that the first derivative is 0 at a particular point. All you have to do then is find out what the value of the second derivative is. Okay, now there's one other thing we didn't cover. Can somebody go shut that? It doesn't have to be you, Jawan. You just happen to be closest to the door. Go ahead, ask me.
ask you what?
Somebody's got to ask me. Well,
What happens when f double prime is 0?
nice question. Thanks, Tiger. All right. What happens if the first derivative equals 0 and the second derivative equals 0? It is an inflection point. That's exactly right. Yes. What was that? No. Go ahead. Go ahead.
I was wrong.
All right. Watch this. Imagine having a slope of 0 and being an inflection point.
Oh, would it be like an unidentified point like the when it's a cubic function?
Yes, that's exactly what it is. And what have we been calling that?
Unidentified.
Not unidentified per se, but what we've been saying, identify it at, say it again?
Neither.
A neither. That's right. That is a neither point. This is a neither point.
So it's neither maximum.
It's neither a maximum nor a minimum. It's not a local maximum. It's not a local minimum. Okay? The only thing that can really happen is if this happens is to have a slope of 0 and an inflection point. Okay? I mean, technically, you could have, I'm trying to think of the best way to say this. I suppose there's a way to have a slope of 0. No, that couldn't happen. That couldn't happen. Yeah, it would have to be, yeah, you couldn't go back to concave down or the whole thing would be concave down. Yeah, it's definitely a neither point. Okay? Does this make sense to you? Okay? The second derivative test, all you have to, please do all the homework problems. I'm telling you, you're going to feel a lot better about it. These are the kinds of questions I can give you. I mean, like what I just showed you, I can say, let's say f prime of 4 is 0 and f double prime of 4 is negative 3. Is this a local minimum, a local maximum, or neither? Okay, it's a local maximum, concave down with a 0 slope. Yes, sir.
That's a weird question I might hear.
Uh-huh.
If there was a vertical tangent line,
Yes. Yes.
how would that be? Would that
Okay.
be considered neither?
A vertical tangent line, no, it wouldn't even be that. It wouldn't be even be in the category because watch, it is a place where f prime of x is undefined. Okay, it is a place where f prime of x is undefined. Okay, and technically speaking, it is an inflection point. Okay, because we are going from concave down to concave up, right? So I would call it an inflection point, but if the first derivative is undefined, then so is the second derivative.
Okay,
Yeah.
I don't expect that to be on a test or anything. I just
Yeah, I mean, look for it. If it's there, it's an inflection point. It is. The main thing with an inflection point is that you have to have continuity, and with a vertical tangent line, you do have continuity. Okay, so I personally would call it an inflection point, but I would probably not rely on simple diagnostics to draw that conclusion. I would probably do an extra thing or two. Like I would find out whether the slope on the left was going to infinity and if the slope on the right was going to infinity or negative infinity. Does that make sense? Yeah. Just to make sure that it was a vertical tangent line and that it's an to identify it as an inflection point. I've never really seen stuff like that on the AP exam though.
I'm just curious.
That's a good question. Keep asking questions like that. Does someone else have a question or is that it?
Could you just talk about it again about how it's a max if the second derivative is negative?
Sure. Second derivative. Would you agree this is concave down?
Yes.
What does that look like on a graph? What's that? Well, sure, but what does this point look like? Does it look like a local minimum or a local maximum? Okay. Just draw, when you know that a graph is concave up, just do this and ask yourself, does that look like a local maximum or a local minimum? What does it look like to you? There you go. So concave up means local minimum. Okay, it never hurts to draw a little tiny piece of a graph to get your bearings. Okay? Is that what you meant by talk about it a little more?
If the second derivative was negative,
If the second derivative is negative, what does that mean about the shape of the graph?
it's a maximum.
Correct, because it's concave down. Yeah.
You drew it right there.
Yeah, and he just wanted to, Apparently the bell is off today.